We're exploring a concept that might honestly sound like standard, dry textbook chemistry at first glance, but actually, it's the invisible language orchestrating our entire physical and biological world. We're talking about polarity. From why water flows the way it does, to how your very DNA holds itself together, polarity is the hidden director pulling all the strings behind the scenes.
Okay, let's dive into this. Here is our roadmap for today. We're going to start with the foundations of chemical polarity, then move into molecular shape and symmetry. After that, we'll hit real-world physical applications, explore the biology of polarity, and finally wrap up with some deep conceptual mysteries.
All right, Section 1, Foundations of Chemical Polarity. Let's start at level 1 and get down to the absolute basics of how atoms interact. As a quick refresher, the core driver of this whole invisible language is electronegativity. You can think of a chemical bond kind of like a game of tug-of-war over shared electrons. Electronegativity is basically just a measure of an atom's strength in that tug-of-war. Its ability to pull those shared electrons toward itself. And here's the kicker. Atoms rarely share equally.
So the crucial point is that this unequal sharing creates a dynamic imbalance. Just looking at the comparison here, on the right you've got two bonded hydrogen atoms. They share perfect electronegativity. Because they're the exact same element, it's a perfectly matched tug-of-war. The sharing is totally equal, which gives us a non-polar bond. But look over on the left. When hydrogen is bonded to chlorine in HCl, well, chlorine has a much higher electronegativity. It aggressively pulls those shared electrons closer to itself, and boom, you've got a polar bond.
Now, to properly read this language, scientists use a specific notation. Take a look at the quick key here on the slide. Notice how that chlorine atom hogs the electrons and becomes slightly negative? We represent that with the Greek letter delta minus, meaning it's electron-rich. Meanwhile, the poor hydrogen atom is left kind of exposed and electron-poor, so it gets marked with a delta plus for a partial positive charge. This separation of charge creates what we call a dipole moment, and scientists actually measure that in a unit called the debye.
Moving right along to Section 2, Molecular Shape and Symmetry. This is level 2, where the three-dimensional geometry of these atoms completely changes the game.
Let's look at a classic foundational puzzle to really test our intermediate understanding here. Carbon dioxide and water both contain polar bonds. The oxygen atoms in both of these molecules are highly electronegative and they pull electrons towards themselves. Yet, water is a heavily polar molecule, while CO2 is completely non-polar. Why is that? Well, it turns out that just having polar bonds doesn't automatically make the entire molecule polar.
And this brilliantly illustrates exactly why. Notice how the linear shape of the CO2 molecule down on the bottom left means the oxygen dipoles perfectly cancel each other out. The oxygen on the left pulls with the exact same force as the oxygen on the right, so you're left with a net dipole of 0. But water, H2O, has a bent shape. And because it's bent, the pull of the oxygen atom doesn't get canceled out by anything pulling in the opposite direction. Those dipoles actually add together, giving us a strongly polar molecule.
So the grand takeaway here is that molecular symmetry can completely eliminate polarity. It all really comes down to VSEPR theory. Basically how lone pairs of electrons force atoms into very specific 3D geometries. Take a molecule like boron trifluoride, or BF3. It has highly polar bonds, but because VSEPR theory dictates that it forms a perfectly flat, symmetrical, trigonal planar shape, all those dipoles cancel out. It becomes totally nonpolar. So yeah, shape matters just as much as the bonds themselves.
Let's step up to Level 3, Section 3, Real-World Physical Applications. We'll see how these microscopic shapes dictate the physical properties of the stuff we interact with every single day.
Let's move to and see how this builds into our everyday reality, driving 3 core physical principles. First up, like dissolves like.
This is exactly why polar water easily dissolves polar salts, but absolutely refuses to mix with nonpolar oils. Second is intermolecular forces. Polarity basically determines how tightly molecules grip onto each other, which directly drives things like boiling and melting points. And third, we have selective permeability. This explains why certain substances, like alcohols, are highly soluble, while strictly nonpolar hydrocarbons just aren't.
Think about this for a second. Why does nail polish remover, acetone, mix so seamlessly with water? Well, it's because polarity isn't just some simple mixing trick. The polar regions of the acetone molecule interact beautifully with the polar water molecules. And those interactions determine everything from the boiling point of the solution to how rapidly different materials, including pharmaceutical drugs, are absorbed into different environments within the human body.
Zooming out even further, we hit Section 4, the biology of polarity. Let's look at how this invisible language literally holds life itself together.
Let's trace the massive biological stakes here step by step. Step 1 is cell membranes. They are ingeniously designed with polar heads facing outward toward the watery environment and nonpolar tails hiding on the inside. That creates the absolute perfect selective barrier for life. Step 2 is protein folding. Proteins literally fold with their nonpolar hydrophobic parts tucked safely into the core, while their polar hydrophilic surfaces face outward. And step 3, DNA stability. That iconic double helix is stabilized by delicate hydrogen bonds, which is a direct result of polarity, thriving in a polar, watery environment.
Just looking at the intricate protein ribbon graphic at the bottom center of the slide, you can see that proteins don't just randomly collapse into a clump. They fold into highly specific functional structures precisely because of how their polar and nonpolar regions react to water. Polarity controls bioavailability, it influences how enzymes recognize their substrates, and really it acts as the master architect for cellular life. Finally, we are entering the expert level, Level 4, Section 5, Deep Conceptual Mysteries. Time to tackle the truly mind-bending questions about nature. At a fundamental physics level, we have to ask, how does quantum mechanics actually explain polarity? When we talk about electron clouds, do they literally distort? Well, the answer lies in molecular orbitals. Polarity isn't just some static, fixed property. It's a highly dynamic, emergent consequence of how molecular orbital interactions create physical charge separation. The probability clouds of electrons are quite literally skewed by the varying nuclear poles of different atoms. It's wild to think about.
So, let me pose an ultimate, deep dive question to you. If polarity just completely disappeared tomorrow, would life still exist? The answer is a resounding no. Absolutely not. Our entire biology relies on these weak collective dipoles. Without them, water would instantly cease to be the universal solvent. Proteins would completely unravel. DNA strands would literally peel apart. These weak, partial charges are, in fact, the hidden organizing principles of life itself.
Now, what's really interesting about this slide is the profound implication it brings up. If molecular polarity is ultimately an emergent consequence of fundamental electromagnetism, could another universe, perhaps one with entirely different fundamental charge distributions, even support chemistry as we know it? It really forces us to realize that the specific way unequal electron sharing manifests in our universe is incredibly special, finely tuned, and literally foundational to everything we perceive.
And so we arrive at our final thoughts. As you look around your world today, remember this. Polarity is not merely unequal electron sharing, it is the invisible language through which molecules recognize, organize, and build the physical and biological world. Which leaves us with one final question to chew on. As our understanding of quantum mechanics continues to evolve, what other invisible languages are currently shaping our reality, just waiting to be discovered?